Hello everyone, welcome to Earth Science. Now Earth Science is of course the study of the Earth, but not just the Earth, the atmosphere, the oceans, our neighbors in space and our solar system. So let's start with Earth itself. Now Earth Science is, why do we study the Earth? What is it about the Earth that we need to know? Well, as far as we know, it's our only home. It's our home planet. And there are some major issues in dealing with preserving the planet the way we want it to be. So let's go through a list of some of the issues. Number one, climate change. We're pumping carbon dioxide and methane into the atmosphere. That's warming the atmosphere, the oceans, and the Earth's surface with some deleterious effects. More storms, droughts, myriad of other effects. Sea level rise. Number two is geohazards. What's a geohazard? Well, it's only a hazard if there's living organisms in the way. So a landslide, an earthquake, a flood, volcanic eruption, that's a geohazard. Number three, resource depletion. That means we're using up stuff. We're using up our metals, we're using up our minerals, we're withdrawing a lot of groundwater, and some of that behavior, some of those things we do, again, have some, present some problems for us, for our environment, and for our survival in that environment. So, environmental degradation is the last issue, and I've already mentioned that. That includes pollution, it includes toxicity, damaging our ecosystems and our landscapes. So here is our planet as seen from space. Here's North America. Oh, I'm sorry, I'm wrong. This is Africa, Horn of Africa, Saudi Arabia. It's a beautiful planet, swirling clouds, blue oceans, land masses, a habitable planet, the Earth on which we live. So the Earth has what we call spheres or subsystems. That's the geosphere, which includes the rock all the way from the Earth's surface down to the center of our planet, the core. So that's the solid stuff, the bones of the Earth, if you will. The hydrosphere is everything water. It's the oceans, rivers, lakes, streams, groundwater, all the way down to the ocean bottom. Very important that we have water. Our planet is the only planet in our solar system that has water in all its forms, liquid, gas, and solid in the form of ice. The atmosphere is that envelope above our planet with which we breathe. The gases that make up our atmosphere are nitrogen, 78%, oxygen, 21%, and a bunch of other gases. The biosphere is a sphere that contains all life, living organisms, us, animals, insects, plants, birds, trees, all that's the biosphere. Now all these spheres, all these subsystems react or interact with each other. When it rains, when liquid water comes out of the atmosphere, it gives moisture to the earth and moisture to the plants that grow within the earth. The root system of a tree is within the earth soil, and the root system gathers moisture from the hydrosphere through the soil into its roots. As animals, we interact, we eat plants, we grow plants, we eat animals, we are friends with animals. So each one of these spheres interacts with the others. Here again is a presentation of the spheres of our planet. the atmosphere, the sky, everything weather-related happens in the atmosphere, mostly within the lowermost layer of the atmosphere that we call the troposphere. It's about 7 miles above the planet. The hydrosphere is water. The geosphere is the Earth's bones, the rock, the soil, all the way from the Earth's surface down to the center of the Earth. It's a solid ball of rock primarily, and as you go deeper towards the center, it gets hotter. The biosphere, all living things. Let me say a little bit more about the hydrosphere. Some scientists include in the hydrosphere what they call the cryosphere, which means water in its solid ice form. Cryo means frozen. So what about these systems in terms of energy exchange? In nature, there is no such thing as an isolated system where no energy or matter is exchanged. Pretty much all systems in nature are closed or open. In a closed system, energy is exchanged, but not matter. For example, our planet is a closed system in terms of receiving energy from the sun, heat and light, but with a few rare exceptions, we don't give off matter. We don't give off chunks of the planet to space, per se. An open system is where both energy and matter exchange with each other or exchange with the environment. So an example would be between, let's say, a forest and a river. A forest will release gases, a river will release water. So there's an open system between the two. Here's just a cool photograph of Earthrise as captured by the Apollo 8 astronauts, I believe in 1968, which really gives us a picture of how amazing it is that we are this beautiful planet with water and clouds. Contrast that with the surface of the moon. Barren, bare, no atmosphere, no liquid water. Maybe it used to have water, not sure, but it sure doesn't have it now, not that we found anyway. Let's talk about the interior of the Earth. The Earth, as I've said, is a solid ball of matter. It is composed of layers. The innermost layer of the Earth is called the core, the inner core, which is solid nickel iron. Very, very hot temperatures at that depth and that density. As you go from the surface of the planet towards the center of the planet, the matter becomes denser, 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 hotter, hotter, hotter. Here's the inner core again, solid, made of nickel and iron primarily. The outer core is liquid, but it's a liquid metal. Again, very, very dense and very, very hot. But it's liquid because it's not quite high enough pressure to condense all that liquid metallic material to a solid form. The inner core is solid because of the extremely high temperatures and densities at that point. And we go up from there to the mantle, which comprises most of the volume of the Earth's planetary or geosphere matter. And then we get to the surface of the Earth eventually. If we look at this cutout, we see that there's, from the top, we have crust. And we have two types of crust. We have continental crust, which are the rocks that form the continental land masses, primarily granitic in composition, which we'll go over later. And the oceanic crust, which is primarily basalt, which we'll again learn about later. Now, the continental crust is not as dense as the ocean crust. The continental crust, however, is thicker as a rule. It can be up to 40, 50, 60 miles thick. The oceanic crust, 7 to 10 miles thick. Okay, but again, this is important to remember. The oceanic crust, primarily made of basalt, is denser, heavier per unit weight than the continental crust. As we go down from there, we go from the crust to what's called the upper mantle. That's this material here. The upper mantle and the crust together comprise what we call the lithosphere. Now the lithosphere, we'll talk more about this later, but the lithosphere is what makes up what we call tectonic plates, which give us the shape and configuration of our ocean basins and our continental landmasses. We'll talk about that again later. Beneath the lithosphere is what we call the asthenosphere. Asthenosphere comes from a Greek word, means weak. So this is a weak layer. It's not really weak. I mean, it's solid rock, solid hot rock, but those conditions of temperature and pressure at that depth in the earth makes the rock just mobile enough so that it can actually move in very, very slow fashion. So this is very important because this stuff moves slowly, maybe an inch per year on average. And on top of this moving layer, we have the lithosphere, which moves with it. So as this stuff moves, so does the lithosphere. Put that together, and that's what creates the motion of tectonic plates. As tectonic plates shift, they're riding on the asthenosphere. The plates can collide, slide opposite each other, or one can slide under the other. That's the basic concept of plate tectonics, which makes up the near surface of our Earth. And then as we go from the asthenosphere, we get into the transition zone and into the lower mantle and so forth. So the lithosphere is about 100 kilometers thick. It's about 60 miles. The upper mantle together is around 660 kilometers, which is roughly 400 miles. Okay, let's go on from there. So here's another picture of what we're already talked about in a little more detail. This illustrates the behavior of tectonic plates. Here's the oceanic lithosphere, which is ocean crust and upper mantle, riding on top of the slow motion asthenosphere. So it's moving in this direction. As it hits this piece of continental crust, continental lithosphere, it begins to slide under. As it's sliding under, we call that subduction. Sub means under, duction means moving. As it moves beneath the continental crust, it forms a depression in the sea floor. That depression is a long linear depression that we call a trench. A trench is a plate boundary that signifies the area where subduction is taking place. So what happens when a plate subducts? As it moves underneath, it gets hotter and denser. As it reaches a certain depth, the water that's dragged down from the ocean along with the rock starts to melt at a certain temperature, a certain pressure. The water starts to go into the hot rock at this depth, and water introduced into hot rock promotes melting. So the rock starts to melt. As it melts, it gets less dense and it starts to rise through the lithosphere. Eventually makes its way closer and closer to the surface. As it rises, the pressure gets less and less. It also starts to cool and solidify. It may solidify completely underneath the surface of the Earth and forms bodies of rock formed from hot melting rock, which we call magma. It forms solid bodies of rock, which we call intrusive rock or plutonic rock. So there's bodies of igneous rock that form from originally molten rock below, which we call magma. As this magma rises, it cools into solid bodies of rock. That type of rock formed in this manner is called igneous rock, I-G-N-E-O-U-S. If it makes it all the way to the surface as hot molten rock, the magma we now call lava if it reaches the Earth's surface, and it can erupt through the Earth's surface as a volcano. So this is all to say that one of the effects of subducting plate underneath the continental plate is that it can form a chain of volcanoes from melting rock rising to the surface. That's called a continental volcanic arc. Okay? So what about us? We have a relationship with this planet. So here's humanity and Earth. What do we do with the Earth? Well, we found through our thousands of years of existence on this planet that we need certain things from the Earth in order to survive and build and derive energy. Those are called resources. Let's start at the bottom. We have energy resources. We have petroleum, oil, we have coal, and we have natural gas. Collectively, these are all called fossil fuels, which means they're derived from ancient life forms, in the case of petroleum, from ancient trillions of marine organisms which fell to the bottom of the sea and decomposed and became petroleum. Coal is from decayed plant matter, and natural gas is associated with both petroleum and coal. So we use a lot of this stuff. Per person, we use 7,700 pounds per year of oil, 8,000 pounds of coal. We use a lot of metallic resources. We use iron, aluminum, copper, lead, manganese, zinc, other metals. And we use non-metallic resources, stone, sand, gravel, cement, clays, salt. Okay? So we use a lot of resources. That's one aspect of our relationship with this planet, is we derive resources from it. We need a lot of energy to keep up our modern lifestyle. If we look at the energy we use, of that energy, 40% of it comes from petroleum, 23% from natural gas, 22% from coal. Smaller slices from nuclear power, renewable energy. So again, most of the energy we use comes from fossil fuels. We're trying to change that because we're finding that fossil fuel burning causes too much carbon dioxide to go into our atmosphere. It also causes a lot of pollution. Renewable energy, we mean biomass, which is burning wood, trees, garbage from waste dumps. Solar, of course, comes from the sun. Wind comes from wind blowing windmills and turning turbine fan blades, which induce a generator to produce electricity. Hydroelectric is energy derived from the motion of water, and geothermal is energy derived from hot rock and hot groundwater from below the surface of the Earth. We don't find this everywhere. We find it only in special places like Iceland, for example. Almost all their heat energy comes from geothermal because they're sitting on top of what's called a volcanic or a mantle hotspot, which pumps a lot of energy from the interior of the Earth. So we cause some problems for ourselves and for our animal fellows, colleagues on this planet. We cut down a lot of forests. We use a lot of wood. In some cases, we practice forestry responsibly and we replace cut forest with new forest that eventually will replace itself. But we don't always do that. A lot of timber harvest is cut and slash and burn and run without adequate protection to replant forest or to reduce erosion or flooding or other problems with stream water and animal habitat. We clog up our waterways with garbage, plastic garbage on the ocean. That's not good for sea life. I was just watching today a short video clip on a television program about, I think it's called Sea Rescue, sponsored by SeaWorld here in San Diego. And they showed a clip of these people saving this humpback whale that was in San Diego Bay. Could barely move because it was all tied up with nets and fishing line and so forth. They were successful in freeing the whale, but you know, this is a real problem. So I've already mentioned pumping carbon dioxide into the atmosphere. This is a look at what the process is. The sun beams down radiation to the Earth's surface. High energy radiation, shortwave radiation. So it's absorbed by the Earth. And the Earth reflects some of it back as long wave or lower energy radiation. This long wave radiation, which is infrared radiation or heat radiation, is absorbed by greenhouse gases like H2O, which is water, carbon dioxide, and methane. These gases trap the heat and re-radiate it back to the surface of the Earth, causing the atmosphere to trap heat and causing, in the long run, raising of Earth's surface temperature, temperature of the ground, and the temperature of the oceans, and that's causing problems. Here's another problem. How'd you like to be this person riding around in his motorcycle in China? I think this is possibly Beijing, China. Horrible, horrible smog problem because they burn or have been burning so much coal to supply their energy needs. So let's be friendlier to the Earth. That's my lesson for today. We're not all going to have a haircut and a hairdo, thankfully, like this guy. But the point of this slide is that, you know, the Earth is a beautiful, beautiful place, and we want to keep it clean. We want to keep it healthy so that we can stay healthy ourselves. Thank you.